and the duration for each talk will be 15 minutes, 10 minutes for talk and 5 minutes for question and answers. Then our first speaker at this session will be Hafize Seda Aydınoğlu from the Department of Medical Services and Techniques Program of Opticianry, Vocational School of Healthcare, Sivas Cumhuriyet University, Sivas, Turkey. The title of talk will be Structural and Morphological Characterization of Nitrogen-doped zinc oxide thin films. Can you hear me, Hafize?
Yes.
Yeah. I leave the stage to you, and you can start. Please share your desktop and PowerPoint slides. Your voice is okay, and you can start. Yeah.
Hello everyone, my name is Seda Aydınoğlu. The title of my presentation is Structural and Morphological Characterization of Nitrogen-doped zinc oxide thin films. First, what is metal oxide? The compounds formed by metals by reacting with oxygen are called metal oxide. Metal oxide, it can be used in various fields, and thanks to its properties such as wide band gaps, good electrical conductivity, optical transmittance, high reflectivity in the infrared region. Metal oxide thin films are materials with wide application areas. The benefit of using metal oxides is that their chemical and electronic properties can be adjusted to allow charge exchange with a wide variety of organic molecules. Why we choose zinc oxide? Zinc oxide is one of the most important materials in metal oxide. Zinc oxide is a direct band natural N-type semiconductor with a wide band gap value approximately 3.3 electrovolt. It has a high Biden energy 60 millielectrovolt. Zinc oxide has high transmittance and low electrical resistance in the visible region. Semiconductor zinc oxide thin films have many uses such as gas sensors, organic wastewater treatments, layers of photovoltaic cells, photodetectors, various electronic and optoelectronic devices, biosensors. Experimental procedure. In this study, N-type silicon was used as substrate. Films were deposited in RF magnetron sputtering system using a zinc oxide target. 5 different films were ground with nitrogen content of 0%, 2.5%, 5%, 7.5%, and 12.5%. All films for plasma generation were done by applying 60-watt power. X-ray diffraction. In the figure, the crystal structures of zinc oxide thin films doped with different nitrogen percentages on the N-type silicon are shown by X-ray diffraction. X-ray measurements were made between 20 and 90 degrees depending on the angle and in a step range of 0.02 degrees. Accordingly, it has been seen that the film are generally zinc oxide with 100 and 002 orientations. As shown in the figure, the orientation 100 was not observed in the sample, which was only bound to 2.5% nitrogen percentage. Using the angle values correspondent to the maximum peaks in the diffraction pattern, and the interplanar distance is calculated from the Bragg's law formula. In the equation, n is the degree of reflection, lambda is the wavelength of the incident beam, DHKL is distance between planes, and theta is the reflection angle of the transmitted beam with the plane. In the calculations, it was taken as lambda 0.154 nanometers. The grain size in the films is calculated from the X-ray diffraction data by using the well-known formula. Where K is a constant, lambda is the wavelength of the X-ray used, theta is the break reflection angle, and beta is the half maximum width of the reflection in radians. For calculations, K constant is taken as 0.9. Table 1 shows the XRD data result of the samples deposited on silicon. In zinc oxide thin films doped with different nitrogen percentages, observed percentage of nitrogen increased, excluding the undoped, 2 data angle decreased. As seen in the table 1002 orientations, grain size first increased, then decreased, then increased again. As a result, it showed that it behaves in harmony with half maximum width and particle size measured in scan electron microscope. Scan electron microscope. Scan electron microscope analysis was done on surfaces at 10 kilovolt with a working distance of 9 millimeters. Figure 2 shows scan electron microscope secondary surface topographies O, A, B, C, D, E in different nitrogen percentages, doping of 250 nanometer zinc oxide coating on silicon, F grain size divergent graph of images. As clearly be seen from figure 2, in all samples, this spherical grain size morphology was followed. This could be attributed to the formation of a good spudder regime and the energy within the substrate, and the zinc oxide accompanied by nitrogen doping. From A to E, by increasing nitrogen doping, a slight increase in grain size from 32 plus or minus 5 nanometer 241 plus or minus 6 nanometers should be considered. Table to nitrogen doping efficiency by increasing nitrogen concentration of device adjustment with elemental distribution. This means that the adhesion performance of nitrogen increases up to 5%, then drastically decreases down to 39%. This process may be due to the increases coating thickness, so nitrogen can't stick on the surface of zinc oxide even into the crystal structure. By decreasing nanoparticle area that increases from 32 nanometer to 41 nanometer by increasing nitrogen content. Fourier transform infrared spectroscopy. Here we will see the bonds in the structure of molecules. Fourier transform infrared spectra of zinc oxide thin films produced depending on different nitrogen percentage are given in figure 4. As can be seen from the spectra, all the materials produced seem to have a similar spectrum, but with nitrogen entering the film, the peak began to be absorbed at approximately 1,381 per centimeter. This peak is estimated as the zinc nitrogen bond. This situation is also supported in the literature. As can be seen from the Fourier transform infrared spectrum, the results, it has been proven that the materials produced are nitrogen-doped zinc oxide. Two peaks at 1,390 and 1,501 per centimeter nitrogen-doped zinc oxide sample may correspond to figure the vibration of the zinc nitride bonds, representing that the doping of zinc oxide with nitrogen was successful. Conclusions, and finally, X-ray diffraction analysis confirmed that the nitrogen-doped zinc oxide films belong to the hexagonal crystal structure of zinc oxide. The scan electron microscopy measurements showed that the surface morphology of the films changes with nitrogen doping, and nitrogen was observed in FDIR analysis. Thank you for attention.
Thank
Have
you.
a nice day.
Okay, thank you for your nice presentation. So I think you have another presentation also. If anybody have some question, if you have some question, you can write in the chat box of the in the right hand of your screen. And if not, you can switch to your second presentation. At the end of the second presentation, we will ask you maybe some questions. Okay. Do you hear me?
Okay.
Okay. Hafize is sharing the second presentation just now, and I would like to give the information about the title, structural and electrical properties of P-type nickel oxide thin film produced by thermal evaporation on different substrates. Can you share the second presentation? My video is on just now, and also, but I don't have any voices from your side. Can I ask to share the video? My colleague at the host office. It will be started just now. We are waiting, and yes, okay.
Hello, my name is Hafize Seda Aydınoğlu. The table of my presentation, structural and electrical properties of P-type nickel oxide thin films produced by thermal evaporation on different substrates. Experimental details. In this study, 150 nanometer nickel films were deposited by thermal evaporation method. While the sample holder rotates with 10 RPM to due to uniform film thickness. Nickel pellets in tungsten bath with a purity of 99.99% were evaporated with an evaporation power of 300 watt. That was resulted in 0.1 angstrom per second growth rate at a temperature of 30 degrees and a base pressure of approximately 1.96 times 10 over minus 4 Pascal. 3. We used different nature of substrates that were cut into small pieces of 10 mm times 10 mm size: glass, silicon, sapphire, indium phosphate, and gallium arsenide substrates, and no intentional hidden was applied to the substrate holder before or during thin film growth. 4. Following the nickel film, 50 nanometer on the substrate was samples were annealed at 450 degrees centigrade for 2.5 hours in the air to form polyoxides on the nickel oxide layer. 5. While the sample holder rotates with 10 RPM, 15 nanometer of titanium layer were deposited with a purity of 99.99% titanium target by using RF magneton sputtering method with a power of 118 watt that induced 0.3 angstrom per second at a temperature of 33 degrees centigrade and a base pressure of approximately 4 Pascal. We prepared two samples on a glass substrate, 50 nanometer of nickel thin films as a control sample and oxidized nickel film to form nickel oxide film on glass substrate. The XRD results of these samples were presented in Figure 1a. Also, as a prepared nickel red line exhibit amorphous phase formation rather than crystalline nature. The formation of nickel oxide film black line appears with major peaks After annealing the sample at 450 degrees centigrade for 2.5 hours in the air. Three major peaks of nickel oxide sample were observed at 2 theta equals 37.3 degrees, 43.3 degrees, and 62.7 degrees that correspond to the crystal planes of the 111,200 and 220 respectively. This week, nickel oxide intensities or EDS analysis of nickel oxide sample on glass substrate was given in figure 1b with major signals of glass circle 45.1% oxygen, 53.5% nickel, 1.2% and titanium 0.2%. From the XRD patterns and EDS analysis, no other impurity peaks were detected in the sample. Further investigation with the SEM images shown in figure was 1C on which uniform and flat thin film formation was obtained, and the average film thickness of nickel oxide is found to be 45.7 plus or minus 4.6 nanometer. Figure 1D shows an EDS analysis area with elemental atomic percentages. The formation of nickel oxide film on silicon 100 surface, see figure 2A, was successfully obtained. Nickel oxide film peaks at 2 theta equals 37.3 degree, 43.3 degree, and 61.6 degree assigned to the 111,200 and 220 planes are similar with nickel oxide film formation on glass substrate. Here the peaks at 2 theta equals 32.87 degrees, 61.63 degrees, and 68.86 degrees belong to the silicon 100 substrates, and these peaks correspond to the Miller indices of 100, 320, and 400 respectively. The XRD patterns further confirm that the nickel oxide film grows on silicon surface with high purity and not any other phase formations. As seen in figure 2b, there is an additional phase marked with a triangle at 2 theta equals 64.62 degrees, which may assign to nickel aluminide phases. As in figure 2c, the result that the formation of nickel X phosphor and nickel to indium phosphor phases in the structure is possible along with the nickel oxide formation. This study concluded that annealing above 250 degrees centigrade result in nickel ions diffusion into substrate and form nickel to indium phosphor, nickel 3 phosphor, and nickel 2 phosphor phases star marks. As seen in figure 2D, along with the major nickel oxide and gallium arsenide peaks, there are additional peaks at 28.59 degrees and 33.62 degrees, which correspond to nickel arsenide and nickel to gallium arsenide phases score marks. To characterize the film and thickness of samples, the scan and electron microscopy images of obtained nickel oxide is presented in figure 3, in which the lateral view of nickel oxide film on A silicon, B sapphire, C indium phosphide, and these gallium arsenide substrates were present. After oxidize the nickel layer, the surfaces reasonable smooth. We measured the average film thickness of the nickel oxide layer as 62.63 plus or minus 5.39 nanometer, 71.09 plus or minus 4.33 nanometer, 31.23 plus or minus 2.19 nanometer, and 54.21 plus or minus 4.47 nanometer for silicon, sapphire, indium phosphide, and gallium arsenide substrates respectively. The reason for different film thicknesses obtained for nickel oxide probably due to nickel layer interaction with substrates and oxygen. Specifically, nickel diffuses in indium phosphide and gallium arsenide substrates and form nickel X phosphide and nickel to gallium arsenide phases respectively. Electrical properties. Hall effect measurements were made at room temperature to investigate the electrical properties of the films. Van der Pauw's geometry was used to measure Hall voltage and resistance. It was made for films that produced gold context with mask prepared according to Van der Pauw geometry. The formation of the ohmic context was confirmed before the Hall measurements and ohmic contacts were taken. During the measurement, a magnetic field of 0.1 Tesla, 100 nanoamps current, and 5 volt voltage were applied, and results were summarized in Table 1. While the oxygen 2 molecules diffused through the nickel film during the annealing process, statistically the number of the nickel 2 plus ions oxidizes and form nickel 3 plus via share an electron between oxygen and nickel. In this oxidation process, the vacuum of nickel leads to form holes or oxygen orbitals near nickel sites near the surface that creates the p-type semiconductor or nickel oxide film. Conclusions. 1. The structural properties of nickel oxide film was determined as cubic phase with space group of Fm and 3m by X-ray diffraction analysis that revealed two possible formations with sapphire, indium phosphide, and gallium arsenide, and without glass and silicon nickel surface interactions due to any process. Nickel ions diffuse into the sapphire, indium phosphide, and gallium arsenide substrates, and secondary phases of nickel aluminum, nickel X phosphide divided by nickel to indium phosphide, and nickel arsenide divided by nickel to gallium arsenide were formed. 2. Scan electron microscopy images managed to determine the average film thickness that is also effect of nickel surface interactions. 3. Nickel oxide film on glass and sapphire surfaces exhibited a p-type characteristic that was confirmed by Hall effect measurements. Thank you for it.
Thank you, Seda, for your nice presentation. I think we don't have any question just now. I would like to thank again the second speaker, but the third speech by the second speaker is actually from Gazi University, Gazi Photonics. Huda, can you hear me? Please open
Yes.
your voice. Okay, thank
I
you.
can hear. Can you hear me?
Okay, yes, I am also hearing you just now. Thank you for your coming. And Huda is working at the Gazi Photonics Research Center. Yeah, and the title of talk, her title of talk is Sol-Gel spin-coated niobium pentoxide thin film with different thicknesses. Please share, yeah, and also use the presentation mode, and the stage is yours and you can start.
Hello, everybody. I am Hüda Kömürcü. I'm going to make a presentation for my conference paper. And I graduated from Hacettepe University, and I have been working Photonic Application and Research Center since 2018, and I'm doing a master at Gazi University. My topic is Sol-Gel spin-coated niobium pentoxide thin films with different thicknesses. And my presentation have 8 sections, and I say respectively introduction, niobium pentoxide properties, Sol-Gel process, motivations, Sol-Gel spin-coating technique, characterizations, result and conclusions, references. And introductions, tin oxide films are widely used in vast range of electronic and optoelectronic devices. Among these, niobium oxide-based materials used in various applications, and like solar cells, optical waveguides, interference filters, and sensors. And there have at least 3 stable niobium oxide, niobium dioxide, niobium pentoxide. And in this study, we choose niobium pentoxide, and because of the most stable form. And niobium pentoxide are promising candidates for a wide variety of optical and microelectronic applications, such as sensors, electrochromic glass, etc. Niobium pentoxide properties. Niobium pentoxide has important properties, and 1, resistant to acid and base, 2, high refractive index, 3, low extinction coefficient, and 4, high transparency in the UV visual region. And niobium pentoxide is an n-type direct semiconductor and has polymorphic forms, pseudohexagonal, orthorhombic, monoclinic, tetragonal. And why niobium pentoxide? Many different metal oxide thin films are used for a wide variety of optical and microelectronic application. Among these materials, niobium pentoxide today is preferred for electronic and optical application, and because of its stability in air and water, and other resistant to acid and bases. And niobium pentoxide application, solar cells, sensors, smart windows, anti-reflective coatings, optical filters, optical circuits, transparent conductive electrodes. And this figures Sol-Gel spin-coating system, and niobium pentoxide can be prepared by a variety of techniques, and such as electron beam deposition, chemical spray pyrolysis, and sputtering techniques, Sol-Gel system. And in this study, we choose Sol-Gel spin-coating system, and because Sol-Gel spin-coating system has many advantages, and 1, a simple process at room temperature conditions, 2, economical, 3, fast deposition method at low temperatures. And the Sol-Gel technique is very convenient method of obtaining both inorganic and organic materials. And the precursors are used in niobium pentoxide, and 1, metal salt, for example, niobium pentachloride, and 2nd, metal alkoxide, for example, niobium ethoxide. And if you ask why you choose niobium pentachloride, I say niobium pentachloride is cheap. My motivations, niobium pentoxide thin films have been deposited onto the glass and silicon substrates by Sol-Gel spin-coating technique at different thicknesses to investigate the effect of the spin cycles on their structural, morphological, and optical properties. And the morphological and optical properties of niobium pentoxide films were investigated by using the techniques as X-ray diffraction, secondary ion mass spectroscopy, atomic force microscopy, and UV visible spectrometry. And this figure flow chart using deposition of multilayer niobium pentoxide films, and niobium pentachloride was used as a precursor. The solution was made by mixing and 1.6 gram niobium pentachloride with 33.2 milliliter ethanol and 0.68 distilled water at room temperature, and then it was stirred for 24 hours using magnetic stirrer. And then 0.4 milliliter of this solution was dropped onto the silicon and soda lime substrates, and then coated by using a spin coating system having a speed 3,500 rotation for 30 seconds. And why 3,500 rotation? Because the most homogeneous films are produced at a spinning rate of 3,500 RPM. And after deposition, and we center it to dry on heater 120 degrees for 30 minutes, and then the procedure was repeated 2 and 3 times. And characterization and the morphological and optical properties of the niobium pentoxide films were investigated by using the technique as UV visible spectrometer, atomic force microscopy, X-ray diffraction, secondary ion mass spectroscopy. And X-ray diffraction, and all niobium pentoxide films had an amorphous structure, and in order to form niobium pentoxide began to crystallize, and we have to heat it above 450 degrees, but in this study we centered it to dry on heater at 120 degrees. And while orthorhombic phase niobium pentoxide thin films is absorbed at temperature below 900 degrees, and the crystal showed above 1000 degrees monoclinic. Atomic force microscopy, and this table shows niobium pentoxide films RMS degree, and 1 layer 0.17, 2 layers 0.15, 3 layers 0.41, and we see as layer increase and the surface roughness increase. And then since niobium pentoxide thin film generally used for sensor application, and so high surface roughness can positively affect sensor properties. And UV spectrometry and transmittance spectra wavelength range of 200 nanometer and 1000 nanometer to determine the optical properties of multilayer niobium pentoxide, and we see they have fluctuation in the visible range of transmittance spectra, and this may be associated with interference of light on the film air and film substrate interface, and other reason and presence of oxygen vacancies. And figure out the band gaps of niobium pentoxide thin films, and the optical band gap energies 1, 2, and 3 layers of niobium pentoxide thin films are calculated by using tau relations, and it was seen that the band gap of the niobium pentoxide thin films decreases with the spinning cycle from 3.89 electron volt to 3.78 electron volt. And then we conclude as the number of film layer increases, the band gap decreases, as in the literature for oxide-based materials. And finally, secondary ion beam spectroscopy. Secondary ion beam spectroscopy is elemental analysis technique, and that provides atomic homogeneity and surface characteristic with its depth in ppm range. And the secondary ion of niobium and silicon were detected using oxygen gun, and seems sputter flat surface, and crater is formed, and then crater thicknesses, and we measured with stylus profilometer, and then from SIMS analysis, niobium and oxygen elements have exhibited uniform and homogeneity characteristic, and besides, and we determined niobium pentoxide films depth profile, and for 1 layer 68 nanometer 2 layers 116 nanometer, and 3 layers 178 nanometer respectively. And we conclude as a layer increase and the material of niobium pentoxide increase. Result and conclusion, and in 1, 2, and 3 layers of niobium pentoxide, thin films shows amorphous in X-ray diffraction, and niobium pentoxide thin films generally used for sensor application. High surface roughness can positively affect the sensor properties. And then the thickness is determined as 68, 1016 and 1078 nanometer for 1, 2, and 3 layered films by SIMS respectively. Then the optical band gap of the films became narrower from 3.89 electron volt to 3.76 electron volt, and which increases the number of layers. Then transmission spectrum of the films was decreased as the spinning cycles were increased because of presence of oxygen vacancies. And to summarize briefly, it was remarked that the material properties of the niobium pentoxide thin films control film thicknesses, which in turn will affect the optoelectronic device properties. And because the transition metal oxide niobium pentoxide thin films are an optical layer determining the amount of light entering the device.
Thank you, Huda.
Thank you for your attention.
Okay, thank you, Huda, for your nice speech and also nice topic. Your supervisors selected for you. I thank you and your supervisor also for this very nice topic. Anybody have any question here? I don't see some question in the chat box. Maybe somebody have some question, can ask, request, write something. No question. Thanks again and goodbye.
Thanks.
Okay. So the next speaker also is from the Department of Advanced Technology of Gazi University, Mr. Gökhan Gözetçi. The title of talk is Investigation of Quantum Confinement Effect in Ultra-Thin Titanium Dioxide Thin Films. Gökhan is one of the member of organizing committee just now. So he worked hard with preparing paper and also presentations. I congratulate him also. The stage is yours, Gökhan. Please start.
Thank you, Mr. Yaşar, for nice introduction. Hello, everyone. I hope all of you can hear and see me clearly. Before the presentation, I want to introduce myself briefly. I'm Gökhan. My undergraduation is Metallurgical and Material Engineering at Istanbul Technical University, and now I'm a Master of Science student in Advanced Technologies Department at Gazi University. At the same time, I have been working as a researcher at Gazi Application and Research Center for 3 years. As you see, the title of my presentation is Investigation of Quantum Confinement Effect in Ultra-Thin Titanium Dioxide Films. My presentation will include motivation of this study, experimental details, characterization results I'm discussing about them. As a characterization results, I will share with you AFM results, optical results, and finally, I will conclude the presentation. What was the motivation of this study? Titanium dioxide is most used semiconductor material due to high refractive index, wide band gap, chemical composition, chemical stability, and easy deposition in versatile techniques. As it knows, some properties like crystal structure, surface morphology, chemical composition of film thickness has great impact on the optical properties of semiconductor. In this study, we investigated the effect of titanium dioxide film thickness on optical properties. In ultra-thin films, they show that different behavior from bulk materials. Reduction in the size of particles in nanometer range changed the degree of confinement of charge carriers, which affected electronic and optical properties of semiconductor materials. These differences in behavior are caused by confinement effect, and high surface to volume ratio. In bulk materials, charge carriers move freely in all dimensions, and there is no quantum confinement effect. In two-dimensional materials, charge carriers move freely in X and Y directions, but in Z dimensions, they are confined. These structures are called as quantum well or ultra-thin films. In one-dimensional materials, carriers are confined in X and Z directions, but move freely in Y direction. Quantum dots are zero-dimensional materials, and carriers are confined in all directions. When the quantum confinement effect increases, optoelectronic properties of the materials, like band gap structure, can be controlled by utilizing quantum confinement effect by changing the size of structures. As experimental, in this study, we used soda-lime glass as substrates. Glasses were cleaned with soup and isopropyl alcohol, and then dried with nitrogen gases, and loaded the magnetosputting system. After the evacuation of system, titanium dioxide thin films were deposited on glass. During deposition of all samples, sputting power was 150 watts, flow rate of argon 10 sccm, and grow rate was around 0.25 angstrom per second. Titanium dioxide thin films with thicknesses 35, 30, 25, 20, 15, and 10 and 5 nanometers were deposited on glass. Surface morphologies were examined with atomic force microscope. Finally, transmittance results were obtained with UV visible spectrometers. By using transmittance data, band gap values are determined from type plots. The behavior of surface morphology of films at different thickness were examined in 3x3 micrometer array with atomic force microscope. AFM results show us there is no significant change in the surface morphology by decreasing film thickness from 35 nanometer to 5 nanometer, but it seems that surface morphology of titanium dioxide thin films was very smooth with average roughness lower than 0.5 nanometers. In figure 8, it's shown that transmittance of the titanium dioxide films reduces as the thickness increases from 5 nanometers to 35 nanometers. Reduction in transmittance has satisfied the Lambert-Weir law. In this law, T is equal exponential minus A times D, and in this equation, T is transmitted light, D is thickness of the sample, and A is absorption coefficient. With the increase of film thickness, the transmittance decreases slightly because more atoms are present in thicker films, so more states will be available for the photons to be absorbed. The absorption leads to transition of electrons from valence band to conduction band. Titanium dioxide thin films have a low absorbance in the longer wavelength. It's clearly seen that relatively low in absorbance found in the range of 380 nanometers to 800 nanometers. However, titanium dioxide films have high absorption in the UV wavelength region of 250 nanometers to 380 nanometers. As it can be seen in figure 9, the shifts of the absorption edge towards the longer wavelength with increasing film thickness. It indicates a blue shift in thinner films compared to bulk titanium dioxide. This situation is related with quantum confinement effect. The optical band gap can be determined by using torque relation. In this relation, the direct band gap values have been calculated from alpha H-net square versus H-net plots and are shown in figure 10. Corresponding band gaps were obtained by extrapolating the straight portion of the graph on x-axis at y-axis 1, 0. The value of direct optical band gap for sample 7 is 3.91 electron volts, sample 6 is 3.89 electron volts, sample 5 is 3.87 electron volts. Moreover, direct optical band gap of films which are thicker than 15 nanometers are 3.86 electron volts. Like direct band gap calculation, the indirect band gap values have been calculated from alpha H root square versus H plot and are shown figure 11. Corresponding band gaps were obtained by extrapolating the straight portion of the graph on x-axis at y-axis 1, 0. The value of indirect optical band gap for sample 7 is 3.59 electron volt, sample 6 is 3.57 electron volt, sample 5 is 3.53 electron volt. Moreover, indirect optical band gap of films which are thicker than 15 nanometers are 3.50 electron volt. It's known that the band gap determination by torque plot isn't precisely, but I want to highlight that in figures, straight portion of the sample 7, sample 6, and sample 5, which have thicknesses 5, 10, and 15 nanometers respectively, not overlaying each other's. There is a difference between them, but in sample 1 to sample 5, straight portion of the curves are overlaying. These results show us there is no change in band gaps for films which are thicker than 15 nanometers. It means quantum confinement effect is observed just thinner than 15 nanometers. Beyond this thickness, films behave like a bulk material. Change in the band gap according to the radius of nanoparticle can be calculated. The formula which is seen in right side of the slide. As you see, delta band gap is inversely proportional with the square of radius of nanoparticle. We calculated the radius of nanoparticle from 1 nanometer to 35 nanometers, thus delta Eg is 0 after the 10 nanometers. Also, as you see, quantum confinement effect is drastically increased below the 5 nanometers. In certain films, charge carriers move freely in 2 dimensions, but in 3rd dimension, which are nanometeristic, they have very limited movement on and confined. In this study, it has also been observed that with increasing the thickness of the semiconductor thin films, the amount of shift towards the blue region is reduced, which indicates the movement of charge carriers is freer, and thus the quantum confinement effect are reduced. Also, I want to say that in this relation, we just use the first term, because third and second and third term are ignored compared to the first term, because dominant term is its. I want to conclude my presentation. All samples which have thicknesses from 5 nanometers to 35 nanometers have average roughness lower than 0.5 nanometers, and they are perfectly smooth. Films are also transparent in visible region, and transmittance reduces with increasing thickness. Also, absorption edge shifted to blue region within thinner films, and it's correlated with quantum confinement effect. Quantum confinement effect is shown in films which are thinner than 15 nanometers. Beyond this thickness, carriers are moved freely, and quantum confinement effect isn't shown. There is a good correlation between theoretical calculation for band gap values and band gap determination from torque plots. Also, as I come to the end of the presentation, I want to say the following. Controlling the thickness of the semiconductor layers in nanometer dimensions can be very efficient for band gap engineering to make optoelectronic devices. Thanks for your attention. If you have questions, I will be glad to answer them.
Gökhan, for your excellent presentation. I think we have a question from Ebru Shabnam here. Yes, you can write. Excuse me, I couldn't understand why the ln expression on the y-axis while finding the energy band gap should we use such an expression of the Dirac equation?
Yes, I can share with the reference I used in this equation. I think there's no problem with the using ln in expression for calculations. If you want, maybe I will later share with the this expression with you. Thanks for question.
So if you have a question or something, Ebru Hanım, you can ask. I can ask our host to open the voice for you, and you can ask the question again. Can you open the Gökhan, open the slide which we have y-axis while? Yes. Here, here, here is the ln alpha h nu. Yeah.
Yes. Is there any problem? If there's a problem, I want to correct this, but I think there's no problem. With Yaşar, what you want to say that about this?
No, there is no problem. I know, but there is a question. You should ask the question. Maybe the question is clear. Why you use ln in the y-axis in the 12?
I have no answer about that. Sorry.
Because the y-axis, the amount of y-axis is not important for us, you know, because it is arbitrary unit. Yeah. The amount of the x-axis is important because it is energy, and we can observe here the energy shift. But the amount of the y-axis is the position of the absorption, not position of the absorption. It means that it is the intensity, not the energy. And changing the position of the y-axis cannot affect on the amount of the energy in the x-axis. Okay. Okay. So thank you very much, Gökhan. Again, and we are coming to go to the next speaker here. I would like to introduce the next speaker, Hicret Hopoğlu, from the Faculty of Technology, Department of Optical Engineering, Sivas Cumhuriyet University, Sivas, Turkey. Hicret Hanım have two talks. The first one is optical properties of nitrogen doped zinc oxide thin films grown on the N-type silicon and glass substrate. And the second talk is thickness dependence of structural and optical properties of nitrogen doped zinc oxide thin films on the glass. Can you hear me?
Yes.
So you can open the first slide, and I recommend you, because both of the topics are near together, I recommend open this slide and the PowerPoint slides, and after that immediately you can open the second one, and after finishing two presentations we will ask the people to ask questions. Okay, thank you. But I don't have any voice here.
Hello everyone,
Yeah.
My name is Hicret Hopoğlu. The title of my presentation is Optical Properties of Nitrogen-Doped Zinc Oxide Thin Films Grown on N-type silicon and glass substrate. Outline. The compounds formed by metals by reacting with oxygen are called metal oxides. Metal oxides, it can be used in various fields thanks to its properties such as wide band gap, good electrical conductivity, optical transmittance, high reflectivity in the infrared region. Zinc oxide is one of the most important materials in metal oxides. Zinc oxide thin films do not contain toxic substances, are environmentally friendly, easily accessible, convenient, and cost-effective, have been the biggest factor in the increase of zinc oxide use. Zinc oxide in the direct band natural n-type semiconductor with a wide band gap value approximately 3.3 electrovolt. It has high bending energy 60 millielectrovolt. Nitrogen is considered as a promising candidate to produce a shallow acceptor level in zinc oxide, since it has similar radii and electrical structure to oxygen. Therefore, it has been preferred for doping. Experimental procedure. In this study, N-type silicon and glass were used as substrates. Films were deposited in RF magnetron sputtering system using a zinc oxide target at room temperature. Firstly, substrates were placed in acetone field in a small glass container. Substrates cleaned in acetone for 8 to 10 minutes were left to dry. The dentist between the target and the material to be coated was kept constant at 6.2 centimeters. Glass and silicon substrates were placed in the sample loading chamber of the device to produce nitrogen doped zinc oxide films. A zinc oxide target with a thickness of 0.125 and a purity of 99.99% was using for the deposition of thin films. 5 different films were grown with nitrogen content of 0%, 2.5%, 5%, 7.5%, and 12.5%. The pressure of the base before deposition was approximately 10 to the minus 6 torr and approximately 5 times 10 to the minus 3 millitorr was achieved. All films for plasma generation were done by applying 60 watt power. Optical properties. A. Spectrophotometer measurements. In order to determine the optical properties of nitrogen doped zinc oxide film grown, changing the nitrogen ratio between 0% to 12.5% transmittance T% of the films was measured wavelength range of 280 to 700 nanometers at room temperature. In order to ensure that the optical transmittance values of the films independent from the substrate absorption transmittance measurements were done reference to the glass substrate. The transmittance of thin films obtained at different nitrogen regia given is figure 1. It has been observed that as the nitrogen regia increases, the transmittance decreases up to approximately 500 nanometers and then increases. Further investigation about the energy band gap values were made taking into consideration the absorption measurement. Absorption converted into the absorption coefficient by well-known Beer-Lambert laws as given below, where T is transmittance of the thin film and D is the thickness of the film. The relation between the absorption coefficient and the incident photon energy and the band gap of the materials is given by, where B is constant HV photon energy and N is a constant equal to 1 divided by 2 for semiconductor with a direct band gap transition. The energy band gap of the films was found by plotting alpha HV over 2 minus HV, where the slope of this graph intersect the HV axis indicating the band gap energy of the film. As seen in figure 2, it has been observed that the energy band gap varies between 3.281 electrovolt and 3.274 electrovolt. B. Spectrophotometer, spectroscopic ellipsometer. Further detailed optical analysis was made by the spectroscopic ellipsometry technique. It provides information about the optical system that changes the polarization state of the polarized light coming into the material. This technique is an important thin films measurement technology for its non-destructive and sensitive advantages. The change in the polarization state of the electromagnetic wave is determined by the ratio of the complex reflection coefficient and dependent on the PC and delta values known as ellipsometric parameters. Rho equal RP divided by RS equal tangent PC E over I delta. Here rho shows the ratio of the complex reflection coefficient, which is polarized parallel to the incidence plane RP and the complex reflection. The ratio of RP to RS EA, the ratio of the amplitudes gives the expression of the ellipsometric PC parameters. Tangent PC equal RP divided by RS, the phase difference between RP and RS given another ellipsometric parameters delta. In this study, Cauchy model was selected as the model for zinc oxide thin films. Fitting was performed to ensure the agreement between the experimentally obtained PC values and theoretical determined PC values using the Cauchy model. The variation of reflective index is shown in figure 4 on the silicon substrate. As a result, the reflective index was found for each film, and it was observed that the reflective index decreased as the nitrogen ratio increased. It is believed that it is due to the observed differences between the band gap energy values observed in the thin film. On the other hand, observed change in the transmittance might have effect on the observed difference. The title of my second presentation is Thickness Depends on Structural and Optical Properties of Nitrogen-Doped Zinc Oxide Thin Films on Glass. Experimental details. In this study, 5% nitrogen-doped zinc oxide thin films were deposited by RF magneton sputtering on glass substrate. The direct influence of film thickness on the structural and optical properties of zinc oxide thin film is investigated. Deposition parameters for thin films as follows. Argon gas 95%, nitrogen gas 5%, base pressure 10 to the minus 6 torr, working pressure 5 times 10 to the minus 3 millitorr, substrate temperature, room temperature. Zinc oxide films were deposited on glass substrate at the same condition but different thickness and were labeled as NZNO1, NZNO2, NZNO3, NZNO4. Structural properties. The crystalline quality and orientation of the nitrogen zinc oxide thin films have been investigated by means of X-ray diffraction (XRD). Figure 1 shows the X-ray diffraction pattern for zinc oxide thin films with different film thickness. Different thickness of NZNO1 250 nanometers, NZNO2 350 nanometers, NZNO3 450 nanometers, NZNO4 550 nanometers. Thin films were deposited on glass substrate. For all the films, zinc oxide 002 and 004 peak is observed, indicating that the films are polycrystalline with a hexagonal structure. From the peak position of the 002 peak, the green size, the full width at half maximum FWHM, interplanar distance D are calculated. Further analysis is made by green size evaluation. The green size of the crystallines in the films is calculated from the X-ray diffraction data by using the well-known Scherrer formula, where key is a constant, lambda is the wavelength of the X-ray used, data is the Bragg reflection angle, and beta is the half maximum width of the reflections in the radians. For calculations, key constant is taken as 0.9. Figure 1 shows that as the film thickness increases, the diffraction peaks became sharper, their intensity is enhanced, and its location change. This behavior means that residual stress are generated during the deposition process. The interplanar distance of the diffracting plane D were identified using Bragg equation, where n is the order of the different beam, lambda is the wavelength of the X-ray, and theta is the angle between the incoming X-ray and the normal of the diffracting plane. The green size and the crystalline quality increase with the increase of film thickness. Surface morphology. The typical morphology and thickness of the obtained films were also different by the scanning electron microscope, SEM. Figure 2 AD show the representative SEM image of the films. During the deposition of the film, thickness adjustment was made in the system. Film set at 250 and 350 nanometers came out close to the measurements in SEM. However, for 450 and 500 nanometers, the thickness was larger is in SEM. The film with 450 and 550 nanometers thickness, whose films were adjusted during deposition, were thicker than expected. This station is thought to be caused by the change in the standard deviation and relative surface roughness. Optical properties. Spectrophotometer measurements. In order to determine the optical properties of nitrogen-doped zinc oxide films grown changing, the thickness, transmittance, T% of the films was measured wavelength range of 300 to 800 nanometers at room temperature. In order to ensure that the optical transmittance values of the films independent from the substrate absorption, transmittance measurements were done referring to the glass substrate. Figure 2 presents the optical transmittance in the wavelength range of 300 to 800 nanometers for the films. It has been observed that as the thickness increases, the interferences fingers increase. Further investigation about the energy band gap values were made taking into consideration the absorption measurements. Absorption converted into the absorption coefficient by well-known Beer-Lambert laws as given below, where T is the transmittance of the thin film and D is the thickness of the film. The relation between the absorption coefficient and the incident photon energy and the band gap of the materials is given by where B is a constant each photon energy and is a constant equal to 1 divided by 2 for semiconductor with a direct band gap transition. The energy band gap of the film was found by plotting alpha HV over 2 minus HV, where the slope of this graph intersects the HV axis, indicating the band gap energy of the film. The energy band gap is obtained from intercept of the extrapolated linear part of the curve with the energy axis. The optical energy band gap of the film decreased from 3.252 electrovolt to 3.199 electrovolt, as the thickness increased from 250 nanometers to 550 nanometers. The corresponding values of the HV have been given in a table. Results. 1. It has been observed that as the thickness increases, the energy band gap decreases from 3.252 electrovolt to 3.199 electrovolt. 2. It was observed that as the thickness increased, the peak intensities of the zinc oxide increased. Thank you for attention. Have a nice day.
Okay, thank you very much. Any question, please? There was a 2 presentation, but by Hidra Topoglu from Sivas, from beautiful city of Sivas. Please give our very warm respect to our colleague at the Sivas Cumhuriyet University. Any question? There are no questions. Thank you very much.
You're welcome.
Thank you very much. Bye-bye. The next people we are going to start to talk with her is Esra Balci from Department of Physics, Ankara, Hacı Bayram Veli University, Ankara. The title of talk is Synthesis and Optical Characterization of Gadolinium, Gallium Aluminum Oxide, Neodymium Chrome Persistent Phosphorus. Can you hear me, Esra? But your voice is closed just now. You can open your voice.
Yes,
yeah?
I can hear you.
Okay. Please open, use your PowerPoint slide. Yeah, okay. And the stage is yours. Just know you can start.
Okay, thank you. Hello, ladies and gentlemen. My name is Esra, and today I'm going to talk about synthesis and optical characterization of gadolinium, gallium, aluminium oxides with neodymium and chromium doped persistent phosphor. This study is work done in Ghent University in Belgium with Professor Dirk Polman and Dr. Jairendu. This is my outline. Today I'm going to talk about persistent phosphor, why I choose this material, gadolinium, gallium, aluminium oxide, and experimental methods of my synthesis material, and optical characterization of, then I came to conclusion. Let's start my presentation. Luminescent material is fascinating to people for a long time. It's intriguing phenomenon called glowing in the dark phosphors. Persistent phosphor giving off light for a long time without external excitation. This persistent phosphor don't need any excitation for any external excitation for giving off light. It is really important property. Now, as you can see, there's a picture about application of luminescence material. Actually, luminescence material is lots of application in our daily lives. For example, road marking, ICLLTs, extreme condition, toys decoration, safety, photocatalyst, solar, and bioimaging. Actually, bioimaging is important, and our aim is finding the possible candidate might be suitable for bioimaging. As you can see in the left place, some medical techniques to visualize the human body. For example, X-ray radiography, computed tomography, positron emission tomography, single photon emission computed tomography, magnetic resonance imaging, and ultrasound. Actually, these are harmful techniques for human body, but near-infrared bioimaging is a harmless method for imaging the human body and use luminescence materials. So we focus on this topic. Now you are seeing why I choose this material. I start with why I choose gadolinium. Gadolinium has unique magnetic property. If your temperature is below 20 degrees, it behaves as a ferromagnetic material. But if your temperature is above the 20 degrees, it behaves as a paramagnetic material. Actually, it is important property. Now, why I choose neodymium? It has long fluorescence lifetime. It is used for persistent phosphor, and persistent phosphor need to give light for long time. So it is really important property for persistent phosphor, and it has both excitation and emission lie within biological transparency window. The commercialization of affordable. Why I choose chromium? It has a strong interaction with host lattice and sharp emission features with roughly constant wavelengths. Now we came to our synthesis, my synthesis technique. I use microwave assisted solid state synthesis. It has really advantageous technique because as you can see some advantages in here, rapid processing, increased energy efficiency, reduced equipment cost, and affording high yield, high purity products. This technique easily reduced equipment cost because almost everyone has a microwave oven in their home. So if you make some persistent phosphor or if you want to make microwave assisted solid state synthesis, you can easily reach this technique. I talk about the high purity products in next slides. Now we came to synthesis. Actually, microwave assisted duration is changeable. We limited our duration from 20 minutes to 40 minutes. If apply the duration, if your duration is larger than 40 minutes or 45 minutes, maybe your microwave oven or your scientist or your laboratory can be damaged. If you are choose little shorter duration from 20 minutes, maybe your synthesis cannot be happen because it's maybe your oven it's couldn't be reached enough temperature for synthesis. So from our XRD result, we choose 30 minutes for optimum duration for microwave oven. Now you are seeing a picture. This picture is we use stone cube and activated carbon as a protective shelter because we couldn't know how temperature increase in microwave oven. So we use activated carbon and this cube, this stone cube for putting our samples into the microwave oven. Now we came to, you are seeing microwave acid synthesis and solid state reaction synthesis comparison. Actually, I talk about in there high purity products. As you can see, there is little difference, yeah, or it's look like the solid state reaction synthesis material and microwave acid solid state synthesis look like each other. So we can say microwave acid synthesis reached the high purity product. Now you are seeing we developed three type of material. This one gadolinium gallium aluminum oxide with neodymium doped, chromium doped, and both neodymium and chromium doped. And this you are seeing the materials. These are the XRD graphs of our material for chromium doped, neodymium doped, and both neodymium and chromium doped. As you can see, also we compare the for X0, X1, and X2. If you see in here, some new peak is created for X2 because our material is changing and it's normal to change our peaks. It's almost 30 degree for 2 theta axis. Now we came to optical characterization. We used 3 types of spectrometry for make optical characterization. First of them is a portable light detector, our Spec Hero. Actually, it is really portable and it's really little machine. It has also used own software. You can download from internet and you immediately take measurement. Our Spectre, it's portable light detector, as I said. The excitation was performed using 500 nanometer milliwatts and 808 nanometer laser. Wavelength range is actually limited for 900 nanometer to 1700 nanometer. Actually, taking measurement is very easy. As you can see, you are seeing a picture in here. Just put small of your material and use fiber optic cables. You need to keep close the fiber optic cables in your material. So also you need to make some flash or some light on your materials. So you can easily make measurements. You are seeing the graph. This graph is Ben Nimiger's master thesis graph. I compared the results. Actually, this is his study is work done by solid state reaction, and my work done is microwave reaction. You are seeing it's similar. Now we came to second spectrometer, fluorescence spectrometer. As you can see, there are 2 graphs, and emission wavelength peak is around 725 nanometer, and excitation wavelength peak around 430 nanometer. And oops, yeah, the emission of phosphor must also lie on optical window, and the excitation of the phosphor must also lie on biological window. It's important. The light will be more absorbed and less light will be able to excite phosphor. Less excitation means less emission. Now we came to optical characterization for last spectrometer, ocean optic, and you are seeing again graph. Also, we make SEM and EDS measurements, and you are seeing EDS results and weight and atomic percentage and K ratio. we are seeing image of my material. Again, for sample 2, for chromium doped and chromium and neodymium doped. Now we came to conclusion. In this study, we make synthesis with microwave acid solid state synthesis, and we comparison between neodymium and chromium doped material for X0, X1, and X2. Also make optical characterization with different spectrometers. And these are my references. And thank you for your attention. If you have a question, I'm glad to answer your question. Thank you.
Thank you, Asra, for your nice presentation. It was very interesting. Thank you for you and also for your supervisors. Everybody, any question? And Quasi Photonics and our hosts and our people in the scientific and organizing committee also thank you. There are no questions, I think, and also no time for question. Thank you again and goodbye for you. The next speaker is also from Quasi Photonics, Berkcan Erenler, Department of Metallurgy and Material Engineering, Gazi University. The title of talk is Structural and Optical Properties of SNS thin films deposited with sputtering method. Berkcan, okay, I'm seeing your charming face just now, and you.
Hi everyone.
Thank you, Berkcan. Yeah, please share your screen.
Wait a second, sorry. Yeah.
Stage is yours, you can start. Okay.
Yes, thank you. I'm a master student at Gazi University, Metallurgy and Material Engineering, and I work Photonic Application and Research Center. My presentation title is Structural and Optical Properties of Thin Sulfide Thin Films Deposited with Sputtering Method. Outline, introduction and experimental and final section, results and discussion. Thin sulfide, one of the 4,6 compound semiconductors with an orthorhombic structure, is known to have a high theoretical power conversion efficiency of an approximate efficiency of 30% and approximate efficiency when applied as a light absorber layer for solar cell. And it has a band gap energy 1.1 electrovolt to 1.4 electrovolt. It has a high absorption coefficient and appropriate carrier concentration. And thin sulfide constituent elements are inexpensive, earth abundant, and less toxic. Thin sulfide has a thermal and chemical stability and layer structure. Thin sulfide and also potentially has a thermal chemical stability and layer structure, and it has a anisotropy properties. And thin sulfide semiconductor is a potentially useful material for variety of applications, including photovoltaic, optoelectronic, chemical sensors, or solid-state batteries and holographic. Thin sulfide thin films can be grown by various methods, including spray pyrolysis, deposition, chemical vapor transport, atomic layer deposition, thermal evaporation, and radio frequency magnetron sputtering. Among them, the sputtering method has an excellent advantage than other with high rate deposition, mass production ability, single direct step, and uniform film deposition. Schematic illustration of co-sputtering system. Magnetron sputtering method is a vacuum coating process that falls under the category of PVD and is mainly used for depositing metals, alloys, and compound textiles and other materials. A target or precursor that desired to be deposited is bombarded with energetic ions of inert gas like argon and helium. The forceful collision of these energetic ions with the target ejects target metal atoms into the space. These metal atoms are then deposited on the substrate material forming a film. image of co-sputtering system. This system we use our deposition parameters and our substrate, soda lime glass and silicone, power 30 watt RF, substrate temperature 300 degrees Celsius, argon gas pressure 10 to -7 millitorr, flow rate 4.3 ccm. The thicknesses of the ground films on soda lime glass and silicone substrates were found to be 280 nanometer and 295 nanometer by the profilometer measurement. This system belongs to us, Photonic Application and Research Center. And X-ray diffraction section. The crystal structure of tin sulfide thin film was measured using grazing incidence X-ray diffraction by using cobalt K alpha source, and the generator setting were 40 kilovolt and 40 milliampere in the 2 theta angle range from 10 degree to 90 degree. As can seen in figure 4, XRT pattern of tin sulfide films on soda lime glass. It has a sharp main peak. You can see 111 plane, and it is a good sign structure of film. The main reason, the fact that there are more peaks in the film deposit on silicon. You can see the figure 5. Because soda lime glass is amorphous, silicon is crystal, and all the tin sulfide teams showed 111 plane preferred orientation and orthorhombic crystal structure. UV visible section. Figure 6A and B shows optical transmittance spectra and energy band gaps of the tin sulfide tin films. The energy band gap of tin sulfide tin films was calculated by Tauk method and 1.3 electrovolt. Obtained results show that deposited tin sulfide tin films can be used as absorber layer for tin sulfide tin film solar cell. This work supported by Presidency of Turkey, Presidency of Strategy and Budget. Thank you for your attention.
Okay, thank you, Berkcan. Congratulate you for your excellent presentation. Any question, please? There are no questions. Thank you again.
You're welcome.
So, the last presentation is by the PhD student Nadezhda Lubochko from Scientific and Practical Materials Research Center, NAS, at Belarus, Minsk. And Nadezhda, can you hear me? Yes.
Yes, I hear.
Okay.
You hear me?
Yes, I'm hearing you, and
okay.
You can open the video also, and also the PowerPoint slides.
I show slides.
Okay. So I see here Professor Dmitry Karpinsky. Yeah.
Yeah.
I welcome Professor Dmitry from here also. Okay.
Okay. 1 moment, please. You see my presentation?
Yes. You just
okay.
Please choose the full screen or presentation mode.
My name is Nadezhda Lubochko. I from Belarus, Minsk, Scientific and Practical Material Research Center, National Academy of Science in Belarus, and I presentation my thesis potassium and yttrium double tungstate single crystals activated with thulium ions prepared by the modified Czochralski methods, growth and optical properties. Laser source emitting in the 192 micrometer spectral range are of the high interest for a variety of practical applications in medicine, remote sensing, microstructuring of semiconductor materials, and pumping of optical parametrical oscillators.
Nadezhda, sorry, I'm corrupting you. Can you use the first slide? We are seeing the other slides and it freezes. And
sorry.
Then the first slide you can use, and the you can choose the presentation mode.
Okay.
The second one from the.
Okay.
But it's frozen just now again.
Okay.
If it is frozen, you can close the PowerPoint slides and open again the slide, okay?
Okay, okay.
Okay. Okay, it's okay.
I can start?
Yes.
You see my presentation?
Yes, but the same problem are again. If possible, please again choose the full screen or the presentation mode.
Okay.
But the slide, I don't know what's the problem exactly here. Can you change your slides? But there is no changes observed by us here. Maybe you can see your changes in your slides, but there is no changes. Try again, close the slides and open again your slides if possible. Oh, yes. Then just now choose the full screen form. Yes.
Okay.
But if it is the problem of the full screen form, maybe you can choose from the right. No, from the right.
Yes.
Lower right part of your slides. So it doesn't work.
Doesn't work.
So no problem. I think only way is that you close the slide and open again.
Okay.
Okay.
Okay. Do you see my presentation?
No, just a minute, please. There are some maybe some delay between in connection, but we are waiting. but we are seeing just your name in Russia on the screen. Do you share the slides? If you share, use share screen icon on the lower part of the Zoom application.
Okay.
You should choose the PowerPoint slides.
Mm-hmm. Mm.
Hmm. Yes, yes, but no.
No, sorry.
Just in the right. Oh, you choose that again.
Okay.
That's a problem, I think. In the right part, lower right part, we have the same icon. Yeah, in the lower right part.
Uh-huh.
The image in lower right part. Okay.
Okay.
No.
Mm.
Are you trying to? Oh, yes. Okay. It's
see?
okay. It's okay. Don't choose the full form. Yeah.
Okay.
Yeah, it's okay. You can continue. Go on, please.
Mm-hmm. I presentation. My thesis is potassium and yttrium double tungstate single crystals activated with thulium ions prepared by the method Czochralski, growth and optical properties. Introduction. Laser source emitted in the 1 and 9 and 2 micrometer spectral range are of high interest for a variety of practical application in medicine, remote sensing, microstructuring of semiconductor materials, and pumping of optical parametrical oscillators. Interest in thulium-doped crystals is particularly caused by the availability of powerful aluminum-gallium arsenide diode pump sources and cross relaxation process 3H6 plus 3H4, 3,4 F4 plus 3F4 leading to efficient exciting of 3,4 F4 laser levels thus increase the quantum efficiency of the systems. Monoclinic potassium double tungstate crystals activated with the thallium ions attract attention due to relatively high absorption and emission cross-section broad emission bands and the possibility to grow highly activated crystals. The great potential of thallium KUV laser crystals have been already demonstrated is continuous wave, Q switching, and mode locking regimes of operation. Experiment procedure. The solution smell consisting of appropriate metal oxide was prepared by a continuous fusion method from solved and crystal forming components with controlled weight of each components. Thulium oxide was used as the dopant. The process of determination of the temperature concentration characteristics of the solution melt for growing KUV crystals from K2V207 solved has been optimized the main stage of the process. determination of the temperature range of growth, determination of saturation temperature depending on the concentration and crystal forming components, weight of selected crystal when the temperature dropped by 1 degree per arbitrary unit of the solution melt, and optimization of temperature distribution in the solution melt volume. The figure 1 shows photograph of the 3% TM doped KUA single crystals. Growth of the KUA crystals has been carried out at temperatures below the point of the phases transition 985 degree using the oriental crystal seed, which they gradually pull up upon slow cooling of the solution melt. Stoichiometric composition of crystal forming component was fused with a total mass of solution melt of about 1,600–1,800 grams. Gross temperature was in the range 900–985 degrees during the growth process, and overcooling parameter was about 1.5 to 2 degrees. Crystal pooling speed was about 3.5 millimeters. The destination. The weight of the grown crystals was about 600 grams. After determining the optimal chemical composition of the solution melt depending on the required dimension of the mass of the crystal, the mass of the solutions melt, and the temperature range or growths were defined further based on the received data. It is calculate the temperature reduction mode for the whole time of the experiments. In this case, it is necessary to limit the growth rate of each phase to be below optimal value and to keep it constant during the growth time. Failure to meet this condition leads to crystal growth in the form of parallel clusters, twinning block growth, or the appearance of internal mechanical stress leading to cracking of the crystal upon cooling down to room temperature and during mechanical processing. It is determined that the rate of crystal lifting up is a critical parameter for all crystal growth and the structural perfection of the crystals. Thus, for a crucible of 200 to 100 millimeter size, an increase in the rate of lifting more than 3 millimeters per day leads to decrease in crystals perfection as a mesoorientation of blocks increasing by 3–5 times, thus leading to increase in the concentration of defects in the crystals. X-ray diffraction patterns of TM-KUA crystals. The X-ray diffraction measurements were performed for the crystals using high resolution Brook D8 diffractometer occupied with the gallium 022 monochromators and cuprum K alpha 1 radiation. The X-ray patterns confirmed high purity of the crystals had monocline symmetry. Analysis of the diffraction patterns point at the presence of the OKO reflections only, thus confirming monoclinic crystal structure of the crystals with O10 orientation of the crystal. The polarization absorbed spectrum. quality and characteristics of the gross crystals we analyzed using polarized absorption and luminescence measurements. The polarized absorption spectra obtained for the TM3 plus doped KUV crystals at room temperature were registered by a Varian Carey 5000 spectrometer in the spectral range 750, 850 nanometers and 1050 to 2100 nanometers with the spectral bandwidth of 0 and 3 nanometers and 1 nanometers respectively. Two Polish plates with dimensions of 572 cubic millimeters oriented along three principal optical indicatrix axes NG and M and NP. We used the concentration of doping ions the crystal was determined by compression of absorption spectra with data and was found to be 1 and 9 in meters minus 3. The room temperature polarized absorption cross-section spectra of the TMKUW crystals in spectral range 750, 850 nanometers are showed in figure 3. The absorption TM3 plus band in the result of overlapping transition from thermally pupil crystals field component of the 3H6 group thallium state of crystals P sublevels of first thallium excited multiplet 3F4. When the thallium first excited state is considered as upper level, the spectroscopic peculiarities of 6H6, 6F for absorption transition are relevant to evaluation of optical loser related process. All polarization absorption bands consist of several well-resolved components. Also, these are noticeable broadened at room temperature. Next slide. Kinetic of luminescence decay of TMKUW in the region of about 175 micrometers and polarized emission cross-section spectra of the TMKUW crystals in the spectral range of 1500 or 2100 millimeters. The energy gap between the 3F4 TM3 plus excited multiplet at the terminated group 3H6 state is quite large, above 5,500 centimeter minus 1. Consequently, the simultaneous emission of the several host of phonons takes place to bright these involved levels. In this case, the multi-phonon relations efficiency is limited and radiative near transition are expected to be effective. On the other hand, the TM3 plus concentration is 3 atomic person and interionic energy migration and energy capture by trapping centers cannot be excluded, as it is presented in figure 5. The single exponential decay curve was measured for the luminescence originating in the first thallium excited state. The the luminescent decay time of the 3-4 level was estimated to be 1/34 plus minus 0.05 millisecond, and was slightly shorter that of obtained in for low doped TMKW crystal. This suppression of the 3F4 lasers level lifetime is attributed to the concentration quenching. High quantum yield of luminescence from 3F4 level of about 0.9 means that the thallium ions raised into a well-defined local position in KUW hoist and no sufficient dependence in 3F4 relaxation dynamic occurs. And conclusions: high quality TM3 plus KUBO for single crystals were grown by the modified Chukrailsky method. The values of the growth parameters, thermal expansion coefficient, crystal's rotation speed, especially affecting the crystal's quality, were determined and discussed, focusing on the impact on the crystallization front and the structural defects. It was determined that an optimal orientation of the seed growth was 010 with a solution melt weight of about 1,800 gram, giving the crystal mass of about 600 gram. The optical characterization of the crystal determined absorption and emission cross-section spectra indicated high structural and optical quality of the single crystals. Thank you for your attention.
Thank you very much, Nadezhda, for your very excellent presentation.
Thank you.
And we are waiting for question. Any question, please? No question I'm seeing in the. Thank you very much.
Thank you.
As you see, thanks Nadezhda. And as you see, announcing here at the by our college, we will be waiting for everyone at the closing ceremony in hall 1 for the best presentation award. Approximately 25 minutes later, we have some surprises from Optical Society of America there, and we will be waiting for you at hall 1 after 25 minutes. Okay, goodbye for now.
Thank you.